Hi everyone. So, welcome to my brand new channel. This is actually my very first video, so it's not some polished professional production. The goal here is very simple, education and helping other people who are starting out. We'll be looking at ARM Cortex-M assembly programming this video. This is pretty new for a lot of folks, and when I tried to learn it myself, the information was really scattered. I had to dig through a lot of reading and different resources, so I want to put everything I figure out into videos like this, step by step, so it's easier for the next person. So yeah, this channel is all about learning together and helping each other out. I'm not claiming to be an expert, I'm sharing what I've learned the hard way, so you don't have to. If you find this useful, hit like, subscribe, or drop a comment to let me know what you'd like me to cover next. Thanks for watching, and let's jump into the world of ARM Cortex-M assembly together. Before we can write any code, let's set up the tools. Don't worry, it's just two main downloads and you'll be ready to run ARM Cortex-M assembly on your computer. ARM GNU toolchain. The first one, which we need, is from developer.arm.com and is called GNU toolchain, ARM GNU toolchain. And the file which we are looking at, because I'm running on Windows 11, but you can find your here as well, is RM8664. Let me find it out. Yeah, that's the one we need. So you can download it. I have it already. And when you install that tool, I'm gonna stop it. So when you install that tool, and we have to make sure we added the path to environment variables. It's gonna ask you in the end, after the installation, do you want to add the path to the environment variables? You check this checkbox and you press finish. So this is the first tool which we need to install. And the second one is QEMU. So QEMU lets us run Cortex-M firmware on our PC and you don't need any extra hardware. Easiest option is to download the Stefan Well Windows installer, and you can go to download here. That's on qemu.org. Go to download, choose a Windows, come to the 64-bit version. You can get to the latest one, depends on when you're looking at that video. The current date is 12th of September 2025. So you can go to this folder and download the latest one, which I did. So after you download it, you're not gonna be asked to add it to environment variable, which is very important. If you go to the environment variables in your machine, go to the path, you have to edit, and then you have to add it. Just press new and add this path. If you install it on this path and press OK, this is gonna set up for you. The next step is we have to open the terminal and we have to check if everything is installed as should be. So in order to check the RM toolchain, we have to type rm dash gnu rm dash non ab dash as minus minus version, and then you can see it's installed and the version is 14.3. Now the next check which we need to do is to see if the emulator is installed, and you can do that by emu-system-rm and we do version, and then you can see the version is 10.1. Third one, of course, is our editor or IDE. Is we're using VS Code, and this is just for editing a code. We can install VS Code. I think everyone know what VS Code is, and we have it installed already on the machine. Run VS Code, and I'm gonna bring it here. Now, what I did is I already create the folder Cortex-M Hello, and you can create any folder. That's it. Just the tool chain and the QEMU emulator plus VS Code if you like a nice editor. With this, we can assembly, link, and run our very first ARM assembly program. Here we need to create two files. First file is named startup.s. Startup.s. This is our assembly startup file with the vector table and reset handler. And the second file we need to create is linker. It's usually called linker.ld. I'm gonna call it linker-lm3s.ld because this is what we emulate actually. This is the linker script that tells the linker how to lay out memory. This is very important. I'm gonna paste the code because this is easier than writing it manually, and I'm gonna give you the code in the video as well. We can outline every line here so you can understand better what's going on behind the scenes. So let me explain you in more details what's going on. First three lines with syntax unified, CPU is Cortex-M3, .thumb. This tells the assembler we are writing ARM thumb code for a Cortex-M3 CPU and to use the unified syntax style. And the mark section here, this is the interrupt vector table. It always starts at the address 0 in Cortex-M devices. The first word is the initial stack pointer. The second word is the address of our reset handler, which is like main in C. It runs when the chip resets. The rest are handlers for exceptions and interrupts like NMI, hard fault, SysTick. For now, they are all point to default handler, which just loops forever. That way, if one of them fires, the CPU won't go off into random memory. And we have reset handler. Here is the reset handler itself. When the CPU resets, it jumps here. We just branch to our main function. After that, we sit in an infinite loop so execution doesn't continue into garbage. And we have default handler. This is the default handler all the other vector entries point to. It's just an infinite loop, nothing fancy, it's a safe placeholder for unused interrupts. And this is the main function. Now, here's our actual program. This uses a special ARM debug feature called semi-hosting. We move 4 into register R0. So this is the syntax moves R0 4. Then we load R1, this one, with the address of our string message. The instruction bkpt, which is this one, and 0ab triggers a software breakpoint that QEMU catches and turns into console print. Finally, we just branch to ourselves and loop forever. And of course, I wrote this with artificial intelligence just to be a lot clearer. And you can do that as well with any artificial intelligence, such as ChatGPT. There is quite a lot of AI at the moment. And here, the message. This is our string in read only. It's read only memory. It's no terminated. So the semi-hosting code knows where it ends. So, to summarize, the vector table sets up reset and default handlers. Reset handler jumps into our main, and main uses semi-hosting to print a string to the console. That's our first working Cortex-M assembly program running in QEMU. And of course, I just noticed I just paste the start to linker file, so we don't worry about it too much. We come back to startup S and we fix it. Now let's go into linker file, and this file is quite simple. So we have entry point. This tells the linker what symbol is the program's entry. On Cortex-M, after reset, the CPU jumps to the address from the vector table, which points to reset handler. Declaring it here makes the linker keep that symbol and place it correctly. Then what we have is the memory map. So the memory map declares the physical memory regions of our microcontroller model. Flash port line here. Actually, flash is read execute. start at 0, 256 kilobytes, and that's where constants live. This is the RAM. RAM is read, write, execute, start at 0.2 and then zeros, and we have a length of 64K. That's where variables and the stack live. These addresses match the LM3S board model we use in QEMU. The next one is the stack. So we define eStack as the very top of RAM. The first word in the vector table will use this value as the initial MSP, so-called main stack pointer, when the CPU starts up. Now we tell the linker how to place our sections into those memory regions. And this is the vector table at start of the flash. The vector table must be at beginning of flash at address 0.0000, as we saw here. We explicitly place a section named .esr underscore vector at the flash origin and keep this one. Tells the linker do not discard this section even if it looks unused. That prevents the optimizer from stripping our essential vector table. This is the read-only data in flash. So next, we put all executable code. This is .text, .raw data, like string literals. This is actually string literal into flash. These don't need to be writable at runtime. And we have 0 init data in RAM. .bss holds 0 initialized variables. The loader or startup code ensures this region is cleared to zeros before main runs. We also include common symbols here. This is the symbol, which are uninitialized global sum assemblers compilers, emit. And let's have a quick recap. So we have entry. This is the reset handler, marks our entry symbol. Then we have the memory, which defines real addresses for flash and RAM. We have the eStack. The eStack is top of the RAM, used as initial stack pointer. Then we have ISR vector at flash start. This is vector table must be first. That means the vector table must be first. And we have our text plus the raw data. This is live in the flash, and then we have the BSS lives in the RAM and starts 0. The easier way to run it. So let's check if we're in the actual folder. Yes, we are. Let me make sure I save it. Okay, now we have full length. The way I understood I didn't save it is by seeing the length is 0, which means I didn't press Ctrl S to save the file, and this may mislead me later on. Now let me paste the build command. We first call the startup file. So what we do is we create startup.o file. This is done. The next one to go, it's going to be to do the linker file. And this is done. Now we create the bin files and we run by calling firmware l file. Now we can see the text which we set is hello QEMU Cortex-M3. That's it. We've just built and run our very first ARM Cortex-M assembly program. Here is what we did today. We installed the ARM GNU toolchain and QEMU so we can build and run Cortex-M programs without any hardware. We wrote startup file with a proper vector table and reset handler, linked everything together with a simple linker script that defines flash and RAM. And finally, we run the code in QEMU using semi-hosting to print hello QEMU Cortex-M3. That's a big first step, to be honest. We've gone from nothing to a real bare metal program running on an emulated Cortex-M microcontroller. And in the next episode, we'll dive into CPU registers and instructions. We'll learn how to move data around, do some arithmetic, and start writing little loops. Remember, this channel is all about learning together. I'm not making polished professional videos. I'm just sharing what I had to figure out the hard way so it's easier for you. If this helped you, hit like, subscribe, and drop a comment to let me know you got your own Hello QEMU. Or if you struggle with running it, please let me know so I can help you. And thanks for watching, and see you in the next